We could not remember the title of the project that we were given, and so this is our project title. We see that the water is going somewhere. We don't know where it's going, but we can sometimes maybe possibly tell you the height of the water in the tank. What?
You guys, can we carry on that discussion later?
So for measuring water level, we basically put a bunch of things on sticks and then stuck them in water. So we had a potentiometer, which can you see when oh, cool. Okay. We have a potentiometer over here that we attach to a really, really long stick. And at the end of the stick, we have a float. And so that float like rotates an arm that's attached to that potentiometer. And that measures the height of the water. We'll tell you how. And then we also have this laser that we attach to a stick. And on this stick is also a float that is not super visible in here. But basically that laser measures the distance from itself to the float that is floating on the water, and then we can figure out what the height of our water level is, and then log that in our data logger.
Okay, so I will explain how the potentiometer works. So this is how our potentiometer looks like, and basically what it does is that the center of this potentiometer will rotate. So we can attach our float on the end of these sticks, and then when it rotates, it will change the voltage, because in the back of these potentiometers there are three sticks, and these sticks, two of them will connect to the power. So one is positive and one is negative, and then the third one, it will connect to the center of this potentiometers, and when it rotates, that's why it will change the resistance of the current, and that's how it changes the voltage, and then we can convert that voltage into how much it rotates. So this is basically how it works. And so John told us very useful techniques of how to determine which stick is which if we don't have the data sheet. Because, for example, if this resistance is 10 ohm, then if you put the multimeters on these two terminals, and you will read 10 ohm. But if you took your multimeters on these two sticks, you will read maybe 7 or 5, and then if you took these three, you will read 3 or 5. So that's how you kind of determine which stick is which if you don't have the data sheet. So I find that is very useful. And so here is how we set up the potentiometers. So one of the biggest challenges is how to secure this stuff at the edge of our tanks. So eventually we use a plate and then fix it on the edge of the tank using zip tie, and that provides a very secure support. And then and then we just attach the end of the potentiometers with the stick, and this is our flow, and basically this flow will change depending on the water level. Yeah, so that's basically it.
So for the laser, it's a pretty cool thing. So all you have to do is just turn it on and then read what it says. So basically, this sensor work for between 50 to 50 millimeter. That's what we found from Google, and then the response time is quite good. It's 2 milliseconds. And then here's how we attach the sensor to the object that we want it to float, that so it will change when the water level change. So yeah, we attach the laser to a pole, and then we also put something here. So this one will float when the water change, something like that. And then we just write the distance, and then should we do the calibration? Maybe you can do it.
That's what the slide says.
Oh, yeah.
Yeah.
So yeah, after that we do the calibration. We put some, we write something like to measure where um, the water level, and then here's the result.
All right. So to to calibrate our sensors, we started filling up the water at 10 centimeter level from 0 to about 80 centimeters. And we collected this data. So on the Y, we have the height of the water and we have the voltage. And as you can see, we have like a 98 percentile fit, which is pretty good. We also try to fit a polynomial, which increase the R squared value a bit. Yeah, but that's the calibration for the potentiometer. And this is also the calibration for the laser, which was pretty good. One thing we realized for the data we collected on the laser was that the voltage was all over the place. So this is a reading of the actual reading on the laser, which is on the x-axis. That's the distance from the laser to the surface of the water. And you have the height of the water in the y-axis. That was pretty, almost one, which was also a good fit. Now we'll look at the raw the data, the converted data using our calibration. So this is when the water was stable. So you can see that it's pretty stable. You know, like it's around 7 to 6 because I think we left the tube in it, so the height of the water decreased over time. So this is the data we collected. John started just this morning. Uh, as I was saying, the voltage readings we collected on the laser was all over the place. We have the time stamp in the x direction, and you can see there is no change here because it was all over the place. We don't know why. Probably it's not functioning well. I don't know. So this is also the readings of the potentiometer when we're filling the water. And one thing we realized that there was some offsets here, which we probably need to correct for, but it's starting below 0. But you can see that there is some, these are all the wait times. So we fill it to 10 and we wait for a while and we increase it, and we can see the steps in the data very clearly. This is also when we're draining the water, and you can see some funny thing. We try to put this air gun in the water to see how it's going to vary, and I think that's what is going on here, where you have like the water bouncing all over. So that means that it's pretty sensitive to kind of the surface of the water.
So because we are basically using two different methods to measure the water level, so we can compare the two. So on the x-axis, this is the water level measured by the potentiometer, the rotating arm, and on the y-axis, this is the laser measurement. So and the red line is the one-to-one line. So basically, you can see that they basically have a positive correlation. But the laser measurement are about maybe 1 centimeter smaller than the potentiometer measurement, so there is an offset there. Okay. So anything? Okay, and this is just a view of how we set up our box. So this is the screen, and then we attach two of our sensors to two of our terminals, so we need to read two different readings, one from the laser and one from the potentiometers, but the laser one doesn't really work as you see in Ido's Kobe's presentation. The readings was all over the places, but the potentiometers one was fine, and then we can get our data from the USB port over there. Okay.
I don't know that they require very much explaining, but this is us working
Yeah.
very diligently. This is John helping us cut something. I can't tell what it is. Oh, is it the stick thing? Okay, cool. Oh yes, and Mike helped us effectively use a chainsaw when we needed scissors. We bolted the laser to this pole when we like totally could have used zip ties, but it was really fun, so it's okay. It's very stable. It'll stay there forever. What are you drilling here? I
Yeah,
literally
think we're
can't
drilling
see.
the holes in there.
Oh, in this
Yeah.
thing.
hmm
Do the tapping.
Oh.
Yep.
Cool.
Yeah.
This is yeah. It was very fun. But that is our presentation. Yeah. Alex. Which funny looking measurements? We have
The
many.
laser.
Oh yeah.
Okay, so what exactly we are using here?
Okay, so the laser, right, does a lot of things. One thing that it does is it like reads through a little screen that's on the laser the distance between the laser and whatever shiny thing it's reflecting off of, right? But the other thing that it does is it records the voltage at that reading. But if you like could not sit inside of the water tank and read what the laser was measuring, which is basically what we were doing, you would want to use the voltage and convert it to a distance. But for our purposes, that was useless because it looked like this. So basically, the laser worked, but it didn't work, if that makes sense.
So you were shining the laser into the water.
We were shining the laser onto this little square thing. So you see, can you see that? The little red dot? That's the laser. So this is the source of the laser, and then it's shooting down and pointing right here. So it's recording that distance.
What do you think went wrong?
I don't
Why
know.
does it look like that?
It's a question for the universe to answer.
Probably.
Oh, was this working before? Was this
It was
working
working.
wonderfully?
At some point.
When
A group used
when did it stop working?
A group used it, I think, 2 workshops ago.
Oh.
I mean, you're asking all the right questions. Those are literally the questions.
I know, I did that on purpose. That was the joke.
Seemed like a similar response when we had a wire messed up.
Yeah,
Maybe
it
while
could've
we
been-
were moving it into the welding area, something happened.
That you guys messed our stuff up, or we messed our own
Just
stuff
like
up?
some wire got jostled while it was being transported.
It's possible.
Ready to just kick David right under the bus there.
He kicked himself under the bus.
So on your potentiometer calibration,
Yes.
did you expect it to be, or what did you expect it to look like? Was it going to be linear? Was it going to be nonlinear? Why would it be nonlinear?
Gonna be nonlinear.
Yeah, because this is measuring the angle, right? But we are actually measuring the distance. So we are approximating a straight line with the curve. Yeah. So on the curve here, so this is the voltage,
Then nonlinear.
and that's the
Nothing.
that's the
This-
height of water.
Yeah.
Yeah.
This one, okay.
Mhm.
And you can see that the dots basically form a curve, and this is because you are actually measuring the rotation. So when the water changes to a certain level, it is actually going to decrease less and less in your rotation, or more and more anyway. So initially we fit it with a straight line, but we find out that we need to fit it with a polynomial to account for that. So after we account for the polynomial, we can get a better agreement with the measurement from the laser.
I'm gonna follow it up and ask you some basic math questions. When you have a rotation, why would you expect a rotation to fit to a polynomial? Can you calculate what the relationship should be?
That's the thing we should do if we would do this experiment the second time. We can convert how much it rotates to how much it drops. That conversion is certainly doable, but we just realized that
It wasn't straight.
it's a little bit we need a little bit more calculation for that, and we are lazy.
If you were going to do it, what branch of mathematics would you use? At least, like, what would you expect the calibration to look like if you wanted to drive a calibration equation?
Well,
Trig.
Right.
Yeah. I mean, it looks, you would basically be tracing out a circle, so that's what you would want to use, but again, lazy. And the polynomial fits fine.
Yeah.
Like,
Look like an engineer.
come on, look at that.
You approve.
Other questions?
I have another question.
Okay.
Since I forced you guys all to do a bunch of extraneous construction with various things, what was your favorite part of the construction methods? Did you like any of them? Would you rather have just done everything with hot glue?
No, I think it's good that we didn't use hot glue for everything. I enjoyed the welding.
Yeah, I think I enjoyed the process from our first idea of attaching a metal to the frame to that part where we go to where we use actually a plastic on the corner. So I enjoyed the process of we brainstorming what should we use. It didn't work, we chose something else, and yeah. So it was fun to find.
Yeah, I find it's because it's very important that your base is secure. So the process of figuring how to make a secure base is I find it interesting. Yeah, eventually we use zip tie, and that is enough. Yeah.